Now it asks to find the acceleration at time t and after 1 second. So as we know, the acceleration is the rate of change of the velocity function. So I take the derivative of my velocity function, and here's my acceleration function. My a got cut off here. So I'm taking the second derivative of the position function, which is this one. And it asks for the acceleration after 1 second. I evaluate it at 1, and I get minus 2.467 feet per second per second. So it's feet per second are the units for the velocity. And then remember, the acceleration is the rate of change of the velocity, so it's feet per second, and that's denoted feet per second squared. We're also supposed to graph all three functions together, the position, velocity, and acceleration functions. So the original position function is this solid black graph. This dashed blue graph is the velocity function. And the dashed red graph is the acceleration function. So notice that the velocity function is 0 where the position function reaches a max or min, just where it's turning around. Likewise, the acceleration function is 0 where the velocity attains a max or min. So this slide is answering the question, when is the object speeding up and slowing down? So remember, since the velocity is a directed value, the term speeding up or slowing down has a little bit different meaning than what we often think of. So if you're just going in one direction in the car and you hit the accelerator, you're speeding up because your velocity is increasing in that direction. But also, speeding up could be putting the car in reverse and gunning it, right? So your velocity is decreasing in the negative direction, but you're still speeding up in that negative direction. So speeding up means when the velocity is positive, meaning that our position is growing, and the acceleration is positive. Or it's when the velocity is negative and the acceleration is negative. So in other words, I'm getting a push in the direction of the particle. They're both the same. So speeding up just does not depend just on the sign of the acceleration, but also on the sign of the velocity. Their signs are the same, means it's speeding up. So we want to compare the acceleration and the velocity and see where they're both the same sign. So we can see that the acceleration and the velocity are both less than 0 between t equals 1 and t equals 2. And again between t equals 5 and t equals 6. The acceleration and the velocity are both greater than 0 between t equals 3 and t equals 4. So that's where it's speeding up. It's slowing down where their signs are opposite. So that's where either the acceleration is less than 0 and the velocity is greater than 0, and that's happening between t equals 0 and t equals 1, and between t equals 4 and t equals 5, or where a of t is greater than 0 and v of t is less than 0, and that's happening between 2 and 3 seconds. So that was an example from physics. An example from economics is something called marginal cost, and that's the derivative of a cost function, production cost often for manufacturing. So this is our cost function, and this is the cost in dollars for a company to produce X pairs of a new line of jeans. The marginal cost is the cost to produce the next pair of genes. So for instance, my cost to produce 100 pair of genes is different than my cost to produce 67 pairs of genes, and not just because I'm producing less genes, but there's other factors that go into manufacturing that actually change other quantities. If I find C prime of 100, the marginal cost at 100, at a production level of 100, is what that is. So if I evaluate this function at 100, it evaluates to 11. So this is giving me how much it costs to produce the 101st pair. So now if we compare that marginal cost to the cost of manufacturing the 101st pair of genes, so the actual cost, so marginal cost is really an estimate, but the actual cost, I would take the cost to produce 101 pairs of genes and subtract the cost to produce 100 pairs of genes, and I get $11.07. So that's telling me how much it costs to produce that 101st pair of genes. So it's looking at the margins, right? Which is, for a small change, what's the change? What's the production cost change? So the derivative has the same interpretation in a whole bunch of different branches of science and social science. A derivative just describes the instantaneous change in a function for a small change in the value that it depends on.